how can enthalpy of formation save time? So one of the things that I'm going to be showing you today is a third way to calculate delta H, and in fact one of the fastest ways to determine the delta H. So far, we've seen that we can do a calorimetry experiment, which would be far the longest way to determine the delta H, but it's actually, I guess, the more experimentally reliable because we're actually doing the experiment there. We can determine the delta H by using Hess's law. Next, we're going to see how we can determine the delta H using standard enthalpy of formation. You're going to see here, first of all, a representation of a thermometer. Well, what do we think the temperature is here? And one of the things that I wanted to highlight is I'd like you to imagine this being a mercury thermometer, that the mercury level has risen up to here, or it could be an alcohol thermometer, but some sort of thermometer where you can see the level of liquid in the thermometer. And then I asked, well, what's the temperature? And I specifically did not put any of the labels, any of the calibration on the thermometer. So, of course, you couldn't tell me what the temperature is. Now, let's say a little bit later in the day, the level of liquid inside the thermometer rose. You could tell me, oh, yeah, the temperature went up, but you couldn't actually tell me what the temperature is. Now, the thing is, the enthalpy of a chemical, the enthalpy of a set of reactants, the enthalpy of a set of products actually cannot be determined directly. We can determine changes in enthalpy. The other thing is, we would like to be able to have a categorization, a litany of data that's associated with different compounds so that we could easily determine a delta H for them. But as I say, you can't just measure what the delta H is for a particular compound. So people who study this came up with an alternative method. And in the same way with a thermometer, as I said, we never know exactly what the temperature is, but we can all agree to use certain conventions. And so one convention was to develop a system where we see, well, where is the level of our mercury or alcohol at 0 degrees Celsius? Now, what defines 0 degrees Celsius? Well, as you probably know, it involves the melting point or the freezing point, if you will, of water. And then we said, well, we'll also measure where that alcohol or mercury level is at 100 degrees Celsius. And in other words, this would be the point at which water is boiling. Now, you perhaps appreciate that there are some conventions here. So this would be at 1 bar, for instance. And actually, even knowing when water boils is a little bit tricky. If you try this experiment, put some water in a pot, put a thermometer in, start heating it on the stove, and you might find that it doesn't seem to boil exactly at 100 degrees Celsius because in part, boiling needs a point of nucleation, and it depends on the kind of pot, and so it can get quite complicated. But just keep it a little simple here. We develop this scale, and then we make these graduations between a 0 and 100. And so now we can all agree on what the temperature is. But on a different planet, they may well have done things completely differently. So in a similar way, we've developed a scale to be able to measure, in a sense, enthalpies, but it's based on a change in enthalpy. So here we go. So in a similar way, we're going to develop what we call an enthalpy of formation scale. So you see in the bottom half of the page here on the right-hand side that I've got the scale. And our 0 point, and there is a 0 point, is right here. But it's, again, arbitrary. Scientists have decided to say, okay, an element in its most stable state will have 0 enthalpy. Now, does it have 0 enthalpy? No, but we're going to set it at 0 because we can reliably measure changes in enthalpy from that standard point. We will look at what is the change in enthalpy to form various compounds from the elements in standard state. So what might this look like? Well, take element 1, react it with element 2, it could be also element 3, and we'll form compound A. We'll say that the delta H for this process is called the change in enthalpy of formation. This is actually a fairly important notation. That F, of course, means something, formation. But there's something else here that you really need to watch for, and that's that knot. And we haven't introduced this before. So that knot represents standard state. In other words, we've agreed that we're going to reference a delta H always under certain conditions. Now, it doesn't mean that we always need to make the measurement under those conditions, but it's just that if we make the measurement outside of those conditions, we need to then change the numbers so that it would be, well, what would be those numbers under those conditions? It's kind of like last semester when we were determining the molar volume of a gas. You measured the molar volume outside of STP conditions, and then you corrected for what it would be at STP. So in a similar way, if we measure the delta H outside of standard state conditions, that's fine, but then you would correct for what would be standard state. So what do I mean by standard state? Well, unfortunately, it's not exactly the same thing as STP. It is 25 degrees Celsius, exactly, or 298 Kelvin. 1 bar if you're dealing with gas, and 1 molar if you're dealing with aqueous solution. So note that just by comparison, STP here, the temperature is equal to 0 degrees Celsius, and the pressure is equal to 1 bar. So there is some overlap, but note the difference in temperature, 25 degrees Celsius. So the idea is that we set our elements at 0 enthalpy, and we see, well, how much energy is either released or taken in forming a compound. Now, of course, if energy is taken in, the process will be endothermic. If the process is resulting in a loss of energy, well then, of course, the process will be exothermic. Now, just as a small comment on the side here, if you're starting from the elements and energy is taken in the form of chemical potential energy to form that compound A, okay, so up here, actually, that gives us a sense of what about that compound and its relative stability compared to its elements. And because energy had to be put into the system, it would actually say that that compound is less stable than its corresponding elements. Less stable actually means more reactive. If you want an analogy, picture the idea that if you take an object that's on the floor and you raise it up to a table, well, now it has the potential to fall down to the floor, whereas the floor is essentially more stable. Conversely, if energy is released in forming a compound, well, then that compound is considered to be more stable compared to its corresponding elements. Lots of things going on here. The other thing that we need to pay attention to is like all of these details are important. So yes, it's the elements that make up the compound, but it has to be the element as it would be at standard state. And I will give you some examples. The other thing is that we need to write this reaction and know the delta H for this reaction for forming only 1 mole of compound. Not 2, not 3, but always 1 mole of the compound at standard state. I'd like you to reflect a minute now. Let's turn the page, and you can see a rather distressed looking test tube, and next to the test tube is in a sense, a summary statement of everything that we just talked about. The standard enthalpy of formation is the amount of energy evolved or absorbed, so it can go either way, but always for 1 mole of compound in its standard state, formed from its constituent elements also in their standard state. And of course, I review again what's meant by standard state. For one, I'd like to remind you, what do we mean by the elements in their most stable form at standard state? So please look at these elements that I've got listed. Key question number 1, we've got sodium, bromine, mercury, carbon, and nitrogen. Now note, I've indicated the state of matter because it's actually kind of important. Which elements are in their most stable form? Well, I hope that you circled these guys. And the idea is that it's got to be the element in its state of matter at 25 degrees Celsius. So that's one thing to reflect on. Usually the pressure wouldn't make that much difference in terms of what state it would be, because normally you're used to thinking about these things at being at approximately 1 bar anyways. So the issue is that sodium at 25 degrees Celsius is a solid, and bromine at 25 degrees Celsius is a liquid. Now, you might be wondering, well, how the heck do I know that? Well, actually, I think you know a lot of these things. And so I'm going to show you right now a periodic table. You may want to grab your formula sheet. I'd like you to remind yourself which elements are solid, which elements are liquid, and which elements are gases at 25 degrees Celsius. And it's actually pretty simple. So at 25 degrees Celsius, and maybe we could kind of color code. So gas is going to be our red. So hydrogen, of course, is a gas. Helium is a gas. Neon, argon, krypton, xenon, radon. So all the noble gases. And of course, nitrogen, oxygen, and fluorine, chlorine are all gases at room temperature, or 25 degrees Celsius. Now let's think about who our liquids are. And as it turns out, there are only two. So that's bromine and, of course, mercury. Now, other things, of course, can be liquid, but not at 25 degrees Celsius and 1 bar pressure. So indeed, it is 1 bar pressure, but usually you're used to thinking about these things at about 1 bar. So then, therefore, everything else, and I'm not going to circle the whole periodic table, but everything else is therefore a solid. So hopefully that guides you a little bit in thinking about what would be the most stable form of the element at standard state. So I'm just going to go back. Now, note we said carbon solid, and normally that would be okay. But as you may remember or know, carbon exists as different allotropes. So an allotrope is a different state of a pure element. So typically, you're writing, if you write it with a pencil, you're writing with carbon graphite. Now, you might think, well, what about coal? It doesn't fit in here. Well, coal is more of an amorphous form of carbon. So we're thinking more the form of carbon in its crystalline state. So actually, graphite is considered to be in a crystalline state, a regular pattern of bonding. Diamond is also an allotrope of carbon. And then finally, there are these things called buckyballs and Buckminster Fullerene balls and rings and things. But these are, of course, the two common allotropes. As it turns out, carbon graphite is the more stable form of carbon. So technically, if we're writing an equation that involves carbon as a delta H of formation, we should use carbon graphite.